In this lecture, we are going to discuss first, product life cycle management, second, robust design, third, quality function deployment, four, Kano model, fifth, phases in design and development, and finally sixth, design for production. Product life cycle management. Product life cycle management is a systematic approach to managing the series of changes a product goes through, from its conception, design, and development, through production and any redesign to its end of life. Also, product life cycle management incorporates everything related to a particular product. That includes data pertaining to production processes, business processes, people, and anything else related to the product. Product lifecycle management software can be used to automate the management of product-related data and integrate the data with other business processes such as enterprise resource planning. Note that a goal of product lifecycle management is to eliminate waste and improve efficiency. For example, product lifecycle management is considered to be an integral part of a lean production. Note that there are three phases of product lifecycle management application. First, beginning of life, which involves design and development. Second, middle of life, which involves working with suppliers and managing product information and warranties. Third, end of life, which involves strategies for product discontinuance, disposal, or recycling. Note that although product life cycle management is generally associated with manufacturing, but the same management structure can be applied to software development and services. Robust design. Some products or services will function as designed only with a narrow range of conditions, while others will perform as designed over a much broader range of conditions. The latter have robust design, which means design that results in products or services that can function over a broad range of conditions. For example, consider a pair of fine leather boots, obviously not made for trekking through mud or snow. Now, consider a pair of heavy rubber boots, just the thing for mud or snow. The rubber boots have a design that is more robust than that of the fine leather boots. The more robust a product or service, the less likely it will fail due to a change in the environment in which it's used or in which it is performed. Hence, the more designers can build robustness into the product or service, the better it should hold up, resulting in a higher level of customer satisfaction, of course. Quality function deployment. Obtaining input from customers is essential to assure that they will want what is offered for sale. Although obtaining input can be informal through discussions with customers. But there is a formal way to document the customer wants. Quality function deployment, shortly QFD, is a structured approach for integrating the voice of the customer into both the product and the service development process. The purpose is to ensure that customer requirements are factored into every aspect of the process. Listening to and understanding the customer is the central feature of quality function deployment. The structure of quality function deployment is based on a set of matrices. The main matrix relates to customer requirements, which means what, and their corresponding technical requirements, which means how. This matrix is illustrated in Figure 1. The matrix provides a structure for data collection. Also, additional features are usually added to the basic matrix to broaden the scope of analysis. Typical additional features include importance weightings and competitive evaluations. A correlational matrix is usually constructed for technical requirements. This can reveal conflicting technical requirements. Note that with additional features, the set of matrices have the form illustrated in Figure 2. It's often referred to as the house of quality because of its house-like appearance. The Kano model. The Kano model is a theory of a product and service design developed by Dr. Noriaki Kano, a Japanese professor who offered a perspective on customer perceptions of quality, different from the traditional view that more is better. And instead, he proposed different categories of quality and posited that understanding them would better position designers to assess and address quality needs. His model provides insights into the attributes that are perceived to be important to customers. The model employs 3 definitions of quality, which are basic quality, performance quality, and excitement quality. Basic quality refers to customer requirements that have only a limited effect on customer satisfaction if present, but lead to dissatisfaction if not present. While performance quality refers to customer requirements that generate satisfaction or dissatisfaction in proportion to their level of functionality and appeal. Excitement quality refers to a feature or attribute that was unexpected by the customer and causes excitement, which means the wow factor. Note that features that are perceived by customers as basic quality result in dissatisfaction if they are missing or at low levels, but don't result in customer satisfaction if they are present, even at high levels. Performance factors can result in satisfaction or dissatisfaction, depending on the degree to which they are present. Excitement factors, because they are unexpected, don't result in dissatisfaction when they are absent or at low levels, but have the potential for disproportionate levels of satisfaction if they are present. Note that over time, features that are excited become performance features, and the performance features soon become basic quality features. It is important to know what we can learn from the Kano model. The lesson of the Kano model is that Design elements that fall into each aspect of quality must first be determined. Once basic needs have been met, additional efforts in those areas would not be pursued. For performance features, cost-benefit analysis comes into play, and these features should be included as long as the benefit exceeds the cost. Excitement features pose somewhat of a challenge. Customers are not likely to indicate excitement factors in surveys because they don't know that they want them. However, small increases in such factors produce disproportional increases in customer satisfaction and generally increase brand loyalty. So it's important for companies to strive to identify and include these features when economically visible. Also, the Kano model can be used in conjunction with quality function deployment as well as in Six Sigma projects. Phases in product design and development. Product design and development generally proceeds in a series of phases. First, visibility analysis. Visibility analysis entails market analysis, which means a demand, and economic analysis, which means development cost and production cost and profit potential, and technical analysis, which means capacity requirements and availability and the skills needed. Second, product specifications. This involves detailed descriptions of what is needed to meet or exceed customer wants and requires collaboration between legal and marketing and operations. Third, process specifications. Once product specifications have been set, attention turns to specifications for the process that will be needed to produce the product. Alternatives must be weighed in terms of cost and availability of resources and profit potential and quality. This involves collaboration between accounting and operations, of course. Fourth, prototype development. With product and process specifications complete, one or a few units are made to see if there are any problems with the product or process specifications. Fifth, design review. At this stage, any necessary changes are made or the project is abandoned. Marketing and finance and engineering and design and operations, all of them collaborate to determine whether to proceed or abandon. Sixth, market test. A market test is used to determine the extent of consumer acceptance. If unsuccessful, the product returns to the design review phase. This phase is handled by marketing. Seventh, product introduction. The new product is promoted, and this phase is also handled by marketing. Finally, eighth, follow-up evaluation. Based on user feedback, changes be made or forecasts refined. This phase is handled by marketing, of course. Designing for production. In this topic, you will learn about design techniques that have greater applicability for the design of products than the design of services. Even so, you will see that they do have some relevance for service design. Topics include concurrent engineering and production requirements. Concurrent engineering. To achieve a smoother transition from product design to production and to decrease product development time, many companies are using simultaneous development or concurrent engineering in its narrowest sense. Concurrent engineering means bringing design and manufacturing engineering people together early in the design phase to simultaneously develop the product and the processes for creating the product. More recently, this concept has been enlarged to include manufacturing personnel, example, materials specialists, and marketing and purchasing personnel in loosely integrated cross-functional teams. In addition, the views of suppliers and customers are frequently sought. The purpose, of course, is to achieve product designs that reflect customer wants as well as manufacturing capabilities. Traditionally, designers develop a new product without any input from manufacturing and then turn over the design to manufacturing, which will then have to develop a process for making the new product. This over-the-wall approach created tremendous challenges for manufacturing, generating numerous conflicts and greatly increasing the time needed to successfully produce a new product. It also contributed to an us versus them mentality. Note that the key advantages of concurrent engineering approach are: first, manufacturing personnel are able to identify production capabilities and capacities. Very often, they have some latitude in design in terms of selecting suitable materials and processes. Knowledge of production capabilities can help in the selection process. In addition, cost and quality considerations can be greatly influenced by design, and conflicts during production can be greatly reduced. Second, design or procurement of critical tooling, some of which might have long lead times, can occur early in the process. This can result in a major shortening of the product development process, which could be a key competitive advantage. Third, the technical visibility of a particular design or a portion of a design can be assessed early on. Again, this can avoid serious problems during production. Fourth, the emphasis can be on problem resolution instead of conflict resolution. However, despite the advantages of concurrent engineering, a number of potential difficulties exist in this co-development approach. Two key ones are the following. First, long-standing boundaries between design and manufacturing can be difficult to overcome. Simply bringing a group of people together and thinking that we'll be able to work together effectively is probably naive. Second, there must be extra communication and flexibility of the process if the process is to work, and these can be difficult to achieve. Hence, managers should plan to devote special attention if this approach is to work. Production requirements. Designers must take into account production capabilities. Design needs to clearly understand the capabilities of production. Examples: equipment, skills, types of materials, schedules, technologies, special abilities. This helps in choosing designs that match capabilities. When opportunities and capabilities don't match, management must consider the potential for expanding or changing capabilities to take advantage of those opportunities. Note that forecasts of future demand can be very useful, supplying information on the timing and the volume of demand and information on demands for new products and services. And in this topic, we have three important concepts, which are design for manufacturing, shortly DFM, and a design for assembly, shortly DFA, and manufacturability. The term design for manufacturing is used to indicate the designing of products that are compatible with an organization's capabilities. Also, a related concept in manufacturing is a design for assembly. A good design must take into account not only how a product will be fabricated, but also how it will be assembled. Design for assembly focuses on reducing the number of parts in an assembly, as well as on the assembly methods and sequence that will be employed. Manufacturability is a key concern for manufactured goods. Ease of fabrication or assembly is important for cost, productivity, and quality. Note that with services, ease of providing the service, cost, productivity, and the quality are of great concern. Also, manufacturability is sometimes used when referring to the ease with which products can be fabricated or assembled.